Here is the problem. We have a system with three unknown parameters: a gain k, a first-order lag with time constant t, and a time delay tau. The transfer function is g of s equals k over 1 plus ts multiplied by e to the minus tau s. We apply a step input of amplitude 2, u of t equals 2 sigma of t. The output is recorded and shown in this graph. Our task: determine k, t, and tau from the measurement. Before we read the graph, let us understand what each parameter does. K is the static gain. Imagine you push the input by 2 units. In steady state, the output will be 2 times k. So k directly tells you how much the output is amplified. T is the time constant. It controls how quickly the output rises. A small t means fast, a large T means slow. Think of it like filling a bathtub. A big bathtub takes longer to fill. And tau is the time delay. It is dead time. The system does nothing at all for tau seconds, then starts responding. Like when you turn a hot water tap, there is a delay before warm water arrives. Let us start with K. Look at the graph. After a long time, the output flattens out at a constant value. This is the steady state. From the graph, the output settles at 4. Now, our input was a step of amplitude 2. For a first-order lag, steady state equals input times k. So 2 times k equals 4. That gives us k equals 2. Next, the time delay tau. Look at the very beginning of the graph. The output stays exactly at 0. It does not move at all. This flat region is the delay. The system has not started responding yet. From the graph, this 0 region lasts until time equals 1 second. At that moment, the curve starts rising, so tau equals 1 second. Now we need to find t. We will use the tangent line method. But first, why does this work? For a first-order lag, the step response rises following an exponential curve. At the very beginning of the rise, the curve is steepest. If you draw a straight line along that steepest slope, it acts like a ruler, measuring the time constant. Mathematically, the initial slope equals the steady-state value divided by t. So a straight line with that slope, starting from tau, will reach the steady-state level exactly t seconds later. That is why the tangent line meets the steady state at time t plus tau. Let us apply this. At time equals tau, which is 1 second, the response starts rising. We draw a tangent line at that point. Following this tangent line upward, it hits the steady-state value of 4 at time equals 3 seconds. So t plus tau equals 3. We already know tau is 1. Therefore, t equals 3 minus 1 equals 2 seconds. Now we have all three parameters. K equals 2, tau equals 1 second, and t equals 2 seconds. Plugging these into the transfer function. G of s equals 2 over 1 plus 2s times e to the minus s. This is a first-order lag with gain 2, time constant 2 seconds, and a 1 second delay. Let us review the 3-step method for reading any first-order step response. Step 1. Read the steady-state value and divide by the input amplitude. That gives k. Step 2. Find where the output first leaves 0. That time is the delay tau. Step 3. Draw a tangent at the start of the rise. Where it hits the steady state gives t plus tau. Subtract tau to get t. 3 simple readings and you have the complete transfer function.